So the question was, you were supposed to describe the motion in words. So let's go ahead and do that first. And then Brandy had a great suggestion yesterday. Let's use these as extra practice for converting graphs. And I do apologize, I have one in your head in here. I just been unable to get it. And I won't do tonight because I'm here till 7 o'clock at the open house. So hopefully before the weekend, we'll get those two, or at least by Monday maybe. So if you were to describe this motion in words, first of all, let's look at this. It says X. That's another way of saying that it's a displacement time graph, right? So what is happening here? And say the first, I don't know, 15, 16, 17 seconds. What's it doing? Which way is it moving? To the right or to the left? To the right. How do you know it's to the right? Because it's in the positive area. Is it at a constant speed for the first 15 or so seconds? How do you know it's at a constant speed? Straight line. So it's moving at a constant speed to the right, and then around just before 20 seconds, about 19 seconds or so, it continues moving right, but it accelerates. It begins to speed up to about there, about 28 seconds or so, which is when it begins to. What'd you say? No, say it again. I think you're right. It's okay. Decelerate, absolutely, yeah, okay. It's okay to be wrong, too. I'm wrong. I've been wrong 3 times already today. It's not even like 9:30 yet. It begins to slow down. What about right there, right at about 35, I guess 36, 37 seconds? What does it do? It stops and it turns around, doesn't it? How do you know it turns around? Because it starts going back down towards 0, right? And would you say that it's speeding up right here? Yeah, speeding up. And then here it kind of just decreases its speed a little bit, right? Okay, so if I were to draw a VT graph of that, I feel the need to sit down. If I were to draw a VT graph, first of all, would the velocity always be positive? Or is there a chance that it could be negative here? I think it could be, right? Let's do this. Okay, so for that first up to about there, constant speed, right? How do I show constant speed? Straight line. Do I know where? How far up here? No. I could figure it out. How would I figure that out, Chris? Area? We're going from D to V. We would find the slope, right? Find the slope of that line, which you could do because there's numbers on here. We would find the slope of that line. We'll ignore that. So I'm going to go straight line like to that. Then what's happening? It speeds up a little bit. How do I show speeding up on a VT graph? Straight up? Like this or like that? Second one. Why the second one, Daniel? Why the second one? Because it's speeding up over time, right? It doesn't just go like from like 15 meters per second to 20 meters per second in 0 time, right? It takes a little bit of time. The slope is gradually increasing. So like that, and it actually speeds up quite a bit, but then it eventually goes to, it starts slowing down around 30, right? So it's going to be like, this should all be one line around 30, and then it actually does what? The slope starts changing. Does it go all the way down to 0? That should be a straight line. Does it go all the way down to 0? I got a yeah and I got a no. Why do you say yeah, Brandy? Exactly. Right there, the slope is 0. Right there, the slope is 0. This is a graph of the slope. It has to go to 0. Here, the slope begins to increase and then just tapers off a little bit, right? So the slope increases, which means the value increases. It's probably continuing at a straight line here, and then it's going to do what? It's going to kind of go like that. Is it increasing in speed here? Or straight line? It's kind of hard to tell, right? It's tough to tell that last little bit. I've never done that graph before. I think I did it right. Did I do it right, do you think? Well, help me out. Oh. Did I do it right, do you think, Anderson?
Yes.
Are you just saying that?
No.
Are you just saying that?
No.
I like playing that game. Okay, now you'll notice this one is a velocity time graph. And right away, Brandy, I can already tell that I am not going to enjoy drawing this graph. Thank you oh so much.
You're welcome.
I guess that's how you feel on some days, right? Yeah. Okay. So in words, what's happening here? Well, the object is starting at about 14 meters per second, right? And is it speeding up? It's speeding up, and would you even say, I'm going to put a straight line out here. I'm going to have to rotate it, but would you say that that line there is, do you think it's straight, or is this thing is this thing changing its speed? Not only is it accelerating, like this is a new one for you. If the VT graph was straight like this one here that I'm shaking around here, then that would mean that the acceleration would be constant. It would be flat acceleration, right? But here, the slope is actually doing what? It's getting a little bit steeper, right? It's a little bit steeper here, and then it actually kind of flattens off. So instead of an acceleration time graph, normally that we're used to seeing like that, it's actually going to be steep and it's actually going to be decreasing. It would actually be an acceleration time graph like that. It would have a jerk factor. The acceleration has a slope that is not zero. A little bit advanced. Blame Brad. Okay, so what is this object doing? Well, it's speeding up, right? Is it going forward? Can you tell, Theron, if it's going forward? Yeah, how do you know? Because it's going up? What if it was down here below? Oops. What if it was down here and going up in the zero area? Would it still be going forward? Like, does going up mean that it's going forward?
No.
No, Daniel? No. Why do you say that?
Just to be different.
Just to be different. You're good at that. Well, you're right. He's right as long as it's above, right? But because it's above zero, that means the velocity is positive, which means it's moving forward or to the right. So in that example that I just erased, like this, what would it be doing? Slowing down. But moving left, right? Yeah, so just be careful, a little caution, that's all. Okay, so it's speeding up to the right for a while here, and then what's happening in this region here? Let's just assume it's a straight line, for sake of ease, right? Let's assume this is a straight line. What is happening here? Is it going backwards? Slowing down to the right. How do you know it's slowing down to the right? You're right. Exactly, the graph is approaching zero. The graph is approaching zero. Here, the velocity is zero, which means it's stopped. So it's moved forward, and then it slowed down, and then it stopped, and then it speeds up again. So what did it do? It moved forward, right? Can we just make it into this? That's what you did? Because it's way too hard if we don't, right? Okay, so it's going like this. Now I'm going back to dt, right? Okay, so it's going to the right. It's positive, and so I think, is that right? I think so. Now, do I need this negative territory down here? I don't think I do. You know why? How come? Because the velocity never goes to zero. So I'm going to make myself some more room. The velocity never goes below zero. So it goes up like this, and then this region here it's slowing down, and then it stopped, and then it speeds up again, doesn't it? That would be the dt graph, I think. I'll check with Anderson again. What do you say?
Yeah.
Are you just saying that?
No. I would be.
You'd just be saying yeah?
Yeah.
To agree with me? Are you just saying that now?
Yeah.
You guys are hard to figure out. Alrighty, so here we are on page 56, and you can follow in the textbook if you like. The answers are in the textbook, as per usual. They do a terrible job. I do a much better job. I've given you the formulas up top there. V equals d over t, a equals delta v over t, and our new friends, vf equals vi plus at, d equals vit plus a half at squared, vf squared equals vi squared plus 2ab, and one that I haven't talked about yet, but I'm sure that you know and love, x equals minus b plus or minus b squared minus 4ac all over 2a, known as the quadratic formula. I'm usually waiting for a round of applause here right now, but doesn't sound like it's coming. Have you seen the derivation for the quadratic formula? Have they shown that to you in math class? Or did they just give you the formula? Or did you block that memory out? Really?
Yeah.
Well, you're missing out on some excitement then.
Really good.
Yeah? Maybe I should YouTube it. I don't know if I've seen it for a lot of years. So. Anyways, let's go to example 7 here. Kitty O'Neill, who is an actual female drag racer, reached a speed of 628 kilometers an hour from rest in 3.72 seconds. How far did she travel in that time? What do we know? We know her initial velocity is 0. We don't? We know her final velocity is 628. You probably already realize that you're going to have to convert that to meters per second, right? And our time is 3.72, and the question is, how far did she travel? So which one has D, VI, VF, and T in it?
All.
All of them? Well, these two certainly do, right? Which one? This one has an A in it. That one has an A in it. What am I going to do? We're going to have to find acceleration, right? There's no way around it. We need the acceleration. Let's convert that 628 first before we forget. So 628 divided by 3.6. I'm going to have to go get my notes. Did you get 174.4? Okay, and I think we've all agreed that we're going to have to get our acceleration, so let's use our new friend VF equals VI plus AT. Final velocity is 174.4. Initial velocity is 0. Acceleration is what we're solving for. And our time is 3.72.
Yeah.
You can use that one too, sure. If you want to be that way. Same thing, right? Now which one? Or does it matter? I don't think it matters, does it? We have to have distance, but can't we use D equals VIT? You want to use that one? I've got the VF squared one on mine. Oh, no, I don't. Or do it? No. I got this one for some reason. I don't think it matters. These are easy, right? Yeah, squared. Do you get a distance of 324?
Yes.
0.3 meters? Relatively easy question, kind of a warm-up. I've read the wrong answer. Instead of doing the math, I relied on my notes here, and Joey caught it. Yep. Is that what you had? And did you think, oh, hey, I'm losing it? I'm so glad Joey asked. This answer's still the same, though, right? Yeah, we didn't work that far? I'm looking pretty close here. You got that one? Okay. My apologies. Sometimes it helps to have the answer sheet in front of you. Sometimes it's better just to do it. Is number 8 any different? What's different about 8? It has an initial velocity, but the logic should be exactly the same. Do you want to try that one? I'll try to make sure I do it right. You go ahead and do it. I'm going to do it right here, and then we'll compare answers at the end. Hello, Miss Small.
Hello. Could I talk to Fernanda for 1 minute?
Sure.
Thank you.
She's popular today. There's the 7.77. Does your answer match mine? 260.8? Oh, am I too fast? Sorry. So as Jason pointed out, the logic is exactly the same. The only small difference is instead of using that 63.9 right there, you have to do that subtraction, right? So here we have a Ferrari going from 20 to 230 in 7.5 seconds. Probably is a little slow, I would say, right? 7.5 seconds is a long time. Okay, you're looking for the distance. All right, both of those are relatively easy. Let's go to number 10. Calculate the acceleration of an airbag if it deploys in 30 milliseconds and moves out a distance of 40 centimeters. Are warning bells going off? Right away, what are you thinking? Oh, I don't like this. Milliseconds, ugh. Centimeters, bah. We're going to have to change those, aren't we? Hopefully your spidey senses were tingling there. So, how do we go from milliseconds to seconds? Divide by 1,000? Because you're right. The prefix milli means 1,000. That's what millimeter, right? How many or milliliters? How many milliliters in a liter? 1,000. Milli means 1,000. So we're gonna take 30 divide by 1,000 and get 0.03 seconds, right? And 40 centimeters, centi means 100, so 0.4 meters. We're looking for acceleration. Which one has, do we know anything else? I know time, I know distance, and I'm looking for acceleration. What else do I know? Anything? Okay? But I got D, Joey. Is VI 0? Well, let's stop and think about that for a second. Yeah. Is the initial velocity 0? Like if this car is driving down the highway at 100 kilometers an hour, can you say that it's 0? What do you think? Oh, it doesn't tell us how fast the car is going, right? But what is that distance? What is that? Like in real terms, what is that distance? If you're driving along at 100 kilometers an hour, does the airbag only move 40 centimeters? Or does it just move 40 centimeters relative from the steering wheel? Exactly. So does it matter how fast the car is going, Jim? No. Because we're talking about the frame of reference. Remember me talking about frame of reference in grade 11? Okay? We're talking about the frame of reference of the moving vehicle. It doesn't matter that it's moving. So Robin's absolutely right. Initial velocity is 0. So what is it going to be? It's going to be d equals VIT plus 1/2 AT squared. It's going to be relatively easy. Initial velocity is 0. 1/2. Oh, we're looking for acceleration. Oh, the d is 0.4. Here we go. And t squared, right? And I know the time. What am I doing? I probably just have
I'm forgetting the time.
But I guess it's time zone.
Pardon me?
That's it, never mind.
Okay. So the acceleration here is going to be 0.4 divided by 1/2 of 0.03 squared. And you're going to have to put big brackets around that to make it work, right? On your calculator? How do you solve for A? Is that what you're asking me? Okay. So I got to step back a bit of math there. Okay, well, first of all, the 0 disappears, right? If you want, Dallas, you can do this, right? You can take 0.03 squared. 0.03 times 0.03 is going to be? I think, right? And then take half of that. Right? And then do that if you want. Pardon me? 3 zeros? Did I miss one? Oh, yeah. Ah. So I need one more 0 in here then, don't I? Does that help, Dallas? $888.9 meters per second squared. Does that seem reasonable for an airbag? It's got to come out of there fast, doesn't it? Like, boom, it's got to be there. Yes, it has an incredible acceleration. All right, example 11. Jane Bond, because we'll get into copyright law if I use another name, runs down the sidewalk accelerating uniformly at a rate of 0.2 meters per second squared from her initial velocity of 3 meters per second. How long will it take Jane to travel a distance of 12 meters? What do we know? 0.2. Initial velocity is 3. And all else, oh, my distance is 12 and I'm trying to solve for t. What's your gut telling you here? Is this going to be trouble or is it going to be easy? Seems easy enough, right? Except one small problem. There's 2 t's in the formula. What does that mean, Joey?
You gotta move it over.
Move it over and cube it. Okay, fair enough. You could just give up. Well, I guess that is an option, but I guess we could simplify this a bit, right? Let's see if we can do any canceling or any multiplying. Could we say something like, well, let's take that 12 to the other side. I'll put a 0 there. And I'm going to have, can I go, generally when we have things like this, don't we usually put the t squared first? Like we put the x squared first in order, right? So 1/2 of 0.2 is going to be 0.1 t squared plus 3t minus 12. Have you guys seen this Desmos thing? No? It's pretty cool. Launch calculator. What's my equation? 0.1 t squared, right? It's probably going to make me use x. So x squared, isn't it 0.1? Didn't I multiply by half?
0.1.
Yeah, I multiply by half, right? Plus 3t minus 12. Plus 3x minus 12? What kind of graph is this? Come on. Oh. What kind of graph is it? Parabola. So when we're solving for t in a parabola, what are they really asking this for? Those things there, right? Which we affectionately call the x-intercepts or the zeros. You're absolutely right. Now, I'm guessing that this particular program will let me solve for that right there, right? Wonder how I do that. Yeah, but I want to do it this way. Oh, right there. Look, I just clicked. 3.57 and 0. That's cool. Or minus 33.57 and 0. How can I have two answers here? Because of that square root thing, right? In physics, what is my graph of? I'm talking about an equation that is t, right? And the d is my y. So my x variable is my t. This is a graph that has time here. In physics, can you have negative time? Negative time doesn't really exist, does it?
Yeah.
Or did it already? Okay, what does that all mean? It means, yeah, I heard someone say it a while back, you can use that Desmos thing if you want, but you're probably going to need to do this, right? X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Oh, golly, this is going to be fun. Minus b. Now, who hasn't seen the quadratic formula ever? Because I always have a couple kids. Everyone's seen quadratic formula? You haven't yet, Anderson? Okay, so Anderson, quickly here. In y equals ax squared plus bx plus c. Okay, when you have a quadratic like this, the letter in front of the x squared is the a, the letter in front of the x is the b, and the number by itself is the c. Okay, and there's the formula. Minus b plus or minus square root b squared minus 4ac all over 2a. Apparently you don't need to worry where that comes from because they don't teach that anymore. Well, they teach you the formula, they don't teach you where it comes from.
They gloss over a lot of things, like how you're supposed to keep it, like as little units and stuff, and switch things over.
Yeah.
You just said that you take the number and
Well, there's a lot of things to cover, right? Maybe I'll find a really boring YouTube video of the derivation of the quadratic formula and I'll post it for you. Yeah, I'm sure that won't be hard to find. Minus b, so I'm going to have minus 3 plus or minus square root of b is 3, so 3 squared minus 4 times a is 0.1, and my c is minus 12. And it's all over 2 times a, which is 0.1. And I really should have more room over here. So I got minus 3 plus or minus. Anybody remember what the thing underneath the square root is called? Anybody remember what that's called? The value under the square root? Oh, yeah? What's it in French? No, I will. Because it'll be almost the same word, because it almost sounds like a French word in English.
well, say it in English.
You say it in French. What, do you think it's like a bad word or something? It's going to like sound like a swear word in English? Discriminant. Yeah, see? I knew I was right. What is it?
What's that last number?
Minus 12. funny guy. I get 3.7 over there. Do you know if the discriminant is bigger than 0, that means that it has at least one root? And if the discriminant is less than 0, it has no roots? Probably, eh? So you're going to get two answers, 3.5 or minus 33.5. How do you get two answers? Let me finish this first, Brandon, my thought, okay? How do you get two answers? You're going to go minus 3 and you're going to add 3.7 and then divide by 0.2. Or if you go minus 3 minus 3.7, then you're going to get a big negative value and you're going to get minus 33.5. Is that what I got on my graph? Brandy, what is your question? Okay. Did I answer it already? Okay. So how long does it take her to cover a distance of 12 meters? The correct answer is 3.5. Is there any meaning at all to the minus 3.5? The only meaning that really you can come up with was if she were to travel back in time, continuing at that acceleration, she would travel 12 meters in reverse if she went that far back in time, which really doesn't mean anything, right? That's your answer, 3.5. So you will need access to the quadratic formula, or you will need access to some sort of quadratic solving device. For me? Desmos.com. I don't have a problem with it. But can I say this, that if you use Desmos.com, you have to at least draw a picture of the graph and then show me the zeros. Does that seem fair? Or print screen maybe and show me how you solve it, right? I'd be good with that.
We're not doing 12 and 13 today, right?
No. I think we're going to leave those. Does that sound fair? You guys are probably tired of me talking anyways.